Hello everyone and welcome back on the second day of the virtual transformer testing conference. My name is Ali Hussein and I will be your moderator for today's session. Just before we start with the first session that we have today, we'll go quickly over our agenda for the second day and then some brief introduction on the speaker for today. So our first session for the second day is SFRA testing or sweep frequency response analysis testing by Dr. Roberts, and then also continuing with Dr. Roberts for DFR and moisture. DFR is the dielectric frequency response testing. After that, joining us Kenneth Petrov from Megar USA for testing bushings at 1 hertz. And last will be integrated test vans for maintenance and diagnosis of power transformers by Dennis Tensov. A brief introduction about our speakers. Dr. Roberts is a product owner from our Megar Sweden factory. He received his master degrees in electrical engineering from Riga Technical University, Latvia in 1995, and his PhD from the Royal Institute of Technology in Sweden in 2001. He's been working for Megar Sweden, or formerly Programma, from 2001 as a application specialist in the field of insulation testing and diagnostics. He also worked as a specialist in the field of high voltage breaker testing and diagnostic for several years. And we have Kenneth Petrov. He is from Megar USA, our Valley Forge manufacturing site in Pennsylvania. Ken has graduated from Western Michigan University and bring both field experience as well as unique experience and skill related to modern requirement of testing methods. He has extensive skills to analyze and resolve complex problems in electrical testing of transformers. And for the last speaker, we have Dennis. He received his bachelor and master degrees in electrical engineering from Novosibirsk State Technical University in Russia in 2002 and 2004 from the University of Aachen in Germany. He have been working with Megar as ultra high frequency partial discharge reduction specialist in high voltage cable, and he has been working with Megar since 2009. Now as a business development manager responsible for transformer testing products. As for the rest of the panelists, we also having here joining us today as well is Ole Benzler, an application specialist engineer who was a speaker for yesterday. He will be joining us as a panelist and might have some answer to your questions for anyone who didn't get the chance to ask about yesterday's topic. And also along with him, Dr. Diego Ropolino, a business development manager and expert or a senior member of IEEE as well, will be joining us as panelists today. And last, before we start, I would like to encourage everyone to please feel free to ask any questions and ensure to answer this question at the Q&A session at the end of each presentation. Thank you everyone for joining us, and we'll start off with Dr. Roberts. Okay, you have the right to share your screen now, Dr. Roberts, please. I believe you are muted, Doctor.
Okay, so you see my screen now?
Yep.
Can you hear me?
Yes, clearly.
Great, all right. Then I can start. So my name is Robert Neymanis, and as Ali mentioned, I am product owner of a couple of products from Megger Danderyd in Sweden. These are Frax and IDAX series, and also VAX high voltage amplifiers. So today I would like to talk about sweep frequency analysis, or SFRA, what it is, what we can do, and how we can do, and what we get for results. Sweep frequency analysis testing basics would be good to start with. Imagining that transformer or any other object can be represented by a complex impedance circuits where capacitances, inductances, resistances are interconnected with each other, making up a net of complex impedance. And this network of complex impedances may have different properties at different frequencies, and these frequencies, peaks or valleys or straight lines, may represent different parts of the given test object. Basically, for today, it will be a transformer. What we can do with this complex impedance of the transformer, we can make a measurement on open windings, we can make a measurement on short circuited secondary windings, and make a measurement of attenuation in a wide frequency range, and see what is the response of the transformer winding. If we see changes in current measurement compared to previous ones, then we can actually conclude that there may have been some changes introduced in the test object, and if we can exclude the test setup issues, then we certainly need to look into the measurement closer and see what has happened with the test object. This method is quite unique, and it is able to detect quite a few winding faults, core faults, and other electromechanical issues in a transformer. It may sound very complex test, but actually the test setup and the measurement hardware is pretty much simple. You have a generator. Let's see if I can have some. We have a generator where we can output variable frequencies from several hertz to megahertz, and we apply this to one end of the transformer winding, and we measure this applied voltage as a reference voltage output. And then on the other side of the transformer winding, we measure what comes out. And out comes like attenuated signal, which we then relate to generator output signal. So setup is very easy, but we can, using this simple setup, detect different issues in the winding, as deformations, displacements, shorted turns. We can detect issues with core-related faults like core movement, missing groundings, presence of screens or missing screens, as well as if transformer itself has been subjected to some I don't know, mechanical impacts so that it has moved inside. So the clamping structures and connections has been moved around and so on. The philosophy of the measurement technology is also rather simple. If we have a new measurement and we have a reference measurement which we can compare and they are the same or with insignificant differences, then everything is fine. We can put transformer back in service. However, the problems start when we don't have this agreement and new measurement is not the same as reference ones. So then we start to dig deeper and then have to investigate what has happened, starting with setup analysis, and then if that turns out good, then we go and analyze what has happened with the transformer itself. So, like I mentioned, these tests are comparative, and best of all, the best case is when we have a reference measurement from the factory, so we can have a sort of fingerprint ready and we can always use it when we do the SFRA sweeps of the transformer. So time-based testing is the best way to do this. If we don't have a reference measurement, but we know that some of the very similar transformer of the same design is in a good shape, we can take this transformer and compare to our transformer which we measure today. But we have to make sure that the designs are the same and we can really compare, because if these are different types of transformers, there is no point of comparing whatsoever. And the last case, which is probably most common one, is that we don't have reference measurements, we don't have a similar transformer with its measurements. So what remains to do is to check how the faces look like. And normally when we compare the faces, even there are certain differences between them, they should look fairly similar. And if we observe what to say, significant differences, then it means something is wrong. The faces should look fairly similar. In order to do that, to make this measurement SFRI, we have a product line called FRAX with our main instrument FRAX 101, which is a small box where we can connect our generator and reference and measurement cables. We can use it using USB connection to computer or wirelessly with Bluetooth antenna. And this hardware piece is run by a software on computer. Well, I will not go through the specifications, but just to mention that we have a little simple model, FRAX 99, which has just lower capacity of battery inside, no Bluetooth, and dynamic range is sort of worse than 101. And the possibility to have a built-in computer is in FRAX 150, which is totally standalone, no computer needed. You can run everything from this box. And basically it is FRAX 101 inside, but here we don't have internal battery or no Bluetooth, since PC requires quite a lot of power to be run with display, so there is no battery and no Bluetooth also. Well, regarding SFRA and its analysis, so like I told, it is comparative tests. We compare the trace taken today with traces taken at the factory or at some point which we can consider as a reference. And we look for different frequency ranges in low frequency responses or open and short secondary sides. We compare the same transformer, like I said, which is the best case. We can compare a similar transformer, like a sister transformer produced at the same time from the same producer. Then we look at the symmetric basis, and of course, we look for new or missing the resonances in the curve. Or in order to make it more or less automatic, there is a possibility to do a correlation analysis in our software using a standard DL/T 911 from 2004. So coming further to how the responses look like. And here in this picture, I have a transformer which is in good shape. So when we observe the curves which we have here, so we have an open circuit measurements of high voltage side. So we have three phases here. I mentioned that phases should look similar, and they do, but for let's say star findings, there may be such a thing that a single dip in one phase and double dips in two phases. So this is perfectly normal, as well as for the short circuit measurement here. But otherwise, when we go at the high frequency range, we see that all phases go practically the same for given type of the measurement. So here we have open circuit measurements, then we have a short circuit, the green one, which is on the top. So we also see the pretty much similar phases and the windings. And then we have low voltage winding also here, measured at open circuit conditions. So similarly, we have three phases in high voltage side and low voltage side, pretty much the same. And this is the case where we actually can use a comparison and see that it's very fine. So, but if we observe something like this, like all phases are all over the place, where we have large deviations in almost all frequency range, this is maybe extreme case. This is totally out of order transformer, but somewhere in the middle lies all the different cases, and you maybe have deviations, large deviations here or here, but not in the whole frequency range. But nevertheless, it means that there is issues when you compare the phases. It applies exactly also if you have a reference measurement. So the reference measurement should also be similar for given phase. So they should be very much on top of each other, not like this. There is quite a few considerations to make in order to get a good sweep frequency test, even if it is setup wise pretty simple, and there should not be much errors you can make. But since we have a test results based on comparison, whether we based on comparison, and we want to make sure that our test setup has no influence on the repeatability. For example, here we have a case where the transformer after service maintenance has been put back has been subjected to putting back in service, but still the measurement of SFRA is done and observed certain discrepancies between the two measurements. And eventually it appears that people have forgotten to connect ground connections to the core. So comparison is essential, and we don't want to have any external issues to influence that. For example, here is an example of how good repeatability could be if different test units were used, like different fraxes, different test persons performs a test at different dates after several short circuit in the generator. And when we see as the results from one day and the other day, so we see perfectly lining up curves, so which means that testing personnel has done a good job, and what is even more, what is like the best result here is that the transformer looks fine. It was not damaged due to short service in the short circuit in the generator. So potential compromising factors when doing the SFRA, I would say there are connection quality, how you ground your cable shields. Of course, the instrument itself with its dynamic range and internal noise floor influence the results. And also the core properties in low frequencies in open circuit tests has to be taken into account. In order to make good connections for Frax products, we have made special clamps which ensure good contact quality, and by tightening you can penetrate the conductive layers. You can connect on flat or round bus bars, and also there is a strain relief, so the BNC cables are quite they are not that robust, so they can easily be broken. So there is a strain relief used in order to not pull the cables. So the clamps are one thing to ensure a good contact. Then another thing is to make a proper shield grounding. And in SIGRI and IEC, in the standards, one has come to agreement that the shield grounding has to be done very straight in a straight line along the bushing surface, as short as possible, as straight as possible. And this is in order to avoid different strange behavior at high frequencies. So for example, the loops like this will not allow you to make a good repeatable measurements when you come next time and make another type of loop. So here I can illustrate the previous importance of shield grounding. We don't have any influence of that at lower frequencies, but above, let's say, 1 megahertz or below that even, we have quite a few differences when we have a good grounding, the blue curve. If we have a poor grounding, we have a red one, and black one is when we don't have any grounding at all. So in this case, in high frequency range, it would not be possible to make any conclusions whether it is transformer problem inside or it is our setup. So always I advise to do according this practice, short, straight line along the bushing surface, like in the picture here. We have a bushing which is sort of not vertical, and then the braid can come into touch with the bushing head. But for Frax ground braids, we have rubber insulation on that, so it is not getting an issue. But you see the straight line down here to the ground point is connected. So this is important. And in order to help with such things as good groundings and no disconnections, in a Frax we have provided automatical ground loop detector, which by pressing a button checks all ground connections, and if everything is fine, you have a green light and you can go on and measure. One thing I can mention that it is not like mandatory to use the ground loop detector. It does not, so to say, make a measurement better in any way. It is more like for making sure that you have done a proper setup. And this is one of the conditions of good and successful measurement and subsequent analysis. And of course, instrument performance of hardware inside makes difference. If internal noise is too high, then we don't see the very large attenuations and so on. So, for example, we need at least minus 100 dB for dynamic range, and the noise floor has to be below that. And Frax has noise floor below 130 dB. So if we have a large transformer and we measure open circuit conditions, we may have very, very, say, large attenuations at SFRI sweep. And in order to properly obtain these results, we have to have a good instrument which allows us to measure this attenuation, not just a simple noise. Like, for example, here, this is not a transformer, this is field verification test, which is also one of the good approaches before you start to measure with your system to verify whether it is in working order. But here it is just an illustration that the Frax can measure at this lower level of minus 100 dB quite well. And there is another brand, the blue one, where we have noise only here, and then the noise disappears somewhere about minus 65 decibels only. So this is this is very poor performance of some other SFRI instrument. So this is anything I would recommend. Then I mentioned that we have a core influence on the SFRI measurements, and this is due to residual magnetization, which we have in core, whether if transformer is just switched off or there have been some tests made on it, like, for example, winding resistance test, which is a DC test, and that magnetizes the core. And if core is magnetized, then we will have different SFRI measurements than if the core would not be magnetized. And this is where I would recommend to always, before SFRI measurement, make sure that transformer core is not magnetized. And if we have different tests to be done on transformers, then SFRI test would be put before any DC tests or anything else. And also the open circuit measurements are, besides the magnetization itself in core, they're also voltage dependent. I would not say that voltage dependency is anything of much of concern now when we normally do the measurements at the same and maximum possible voltage. But nevertheless, I will illustrate it. The magnetization effect on SFRI measurement we can observe as like changes in the response or changes in attenuation. When after winding resistance test, we can have a higher magnitude or less attenuation due to residual magnetization in the core. And when we demagnetize, so we get another picture, another way of looking at the data. Regarding voltage influence, so here are some graphs made on the same transformer, just changing voltages from 0.1 to 10 volts peak to peak. And we see that as the higher the voltage, the more attenuation we observe in the transformer, and then also a little bit different shape of it. So in this case, it is also important to make sure that the voltage level at the test location is the same as the reference measurement. For example, if reference measurement is made at 2.8 volts or something similar, then with the FRAX doing measurement at 10 volts, we will not get exactly the reference curve, even if there are no changes in transformer. So we would have to go back to, say, 2.8 volts. Like, for example, here we have two different curves at 2.8 and 10 volts. So we have some differences here which we observe, which are significant. But if we adjust the voltage up to now Omicron's 2.8 volts, for example, and we adjust FRAX also, so then we obtain the same curve as before, the green one. So that is one of the points to be also taken into account. Also, I mentioned about field verification unit, and this is something which is also put into standards, recommended by the standards to have such a box in order to verify your test hardware integrity, so to speak. So you make a measurement on this box and you expect to have a curve like this. If you don't have a curve like this, then there is something wrong. Most probably it is a cable contacts which are loose, or you have forgotten to connect something, or there is a short circuit between measurement clamp and ground and such things. But the field verification box is essential, and it is actually quite good to make sure that your hardware is working and fine. Then there are graphs which maybe is not that important, but to summarize, the accuracy and repeatability of the SFRS. So we want to ensure that we obtain high repeatability by using high quality instruments, high quality connections and cabling and clamps. So we don't do SFR after DC measurements were done on transformer. We demagnetize the core. We use same voltage for all SFR measurements. If we have different voltage for reference measurements, so we better adjust it for today's measurement. And also good grounding of the shields, straight lines according to standards, and also often overlooked but sometimes very helpful thing is to make a good documentation, making photographs of connections of transformer itself and things like that. And also there are standards to follow, of course, and I will not go into the different analysis given into standards since there are quite a lot of material to be covered, different deviations in different frequency ranges are given in these standards, and they describe what fault it could be if there is like differences in a low frequency range or differences in middle frequency range and so on. So these are the standards which we follow. The first one is DLT 911, which is also describing the correlation functions which are automatically input into Flux software. And then the analysis of different measurement cases in standards from IEC, IEEE guide, as well as from SIGREA. And of course, if there are there could be different internal standards, like ABB has their own, and South Africa ESCOM have their own, but basically they are derived from the SIGREA, IEC, and IEEE guides. And just to summarize what is the difference, there is like a requirements for test object and to test equipment. And we see that there is a dynamic range which is specified, accuracy, how you ground the signal cables, and if self-test is required. And so, well, now I think I will stop at this moment, and let's see if we have any questions.
All right, thank you, Doctor, for presentation. We have a couple of questions.
Can I?
The first question is, it's more of a request rather than a question actually, is can you please share some graph which have fault in winding, like displace or turns damage?
Let's see. This is like an fault where you have a short-circuited winding. You see in a one phase there is a very different response compared to two other phases. I think, okay, I don't have in this presentation any good cases with, but this is like a typical example when you have a short circuit to the winding. what was that? It was power transformer which was energized and put into the short circuit at the low side. So it was.
We have also another question. They asking, please clarify how to identify defects at various parts of a transformer.
Well, then it requires me to go into standards. I don't know if I can. I mean, this is something which needs to be studied by like users and looked at. See. See if I can open a standard here. So here you have a different sections where are different faults, and the core related something is at a low frequency range.
I'm sorry, Doctor, but it seems that you are sharing, or the window you are explaining is not shared.
No,
okay.
Could
you please share the window, the full window, not yes. Okay.
So now you see, I'm sorry,
yeah.
I thought I shared the whole screen of mine. Okay, but now you see the screen.
Yes.
Okay, so this is a standard of IEC, where we see the regions where core defects can be detected in a low frequency range. Then in this range, there is interaction between windings, the winding structure at even higher frequencies, and above like 2 megahertz. Then we have a measurement setup and then grounding leads which influence measurement. And if we have like differences in our measurements in any of these parts, then we can roughly estimate that, okay, if we have an issue here, then it is core. If it is issue here somewhere, then it is more like a winding structure, something related to that.
Right. Another question that we are having is, what is the minimum rating of a transformer that SFRA is applicable?
I would not say that there is like a minimal rating. You can apply SFRA to any transformer, basically. It is, you can apply, if you can use test box, like this field verification box to measure, then you can measure on small transformers, you can measure on big transformers. So I would not see any rating limitations here.
Right, and the last question we are having is, what's the frequency of doing SFRA for transformer? Every year, or just after maintenance, or?
Well, if you do the transformer maintenance and you like disassemble something and then disconnect the windings or change bushings or things like that, then after that I would certainly advise to do that. But otherwise, if transformer is not subjected to any faults or any overhauls or anything, then I mean it could be several years between two tests. So it all depends on owner's strategy, what what is happening. And of course, as soon as there is some issues with transformers, then you do like a number of tests, and SFRI would be one of them as well. So it's difficult to say every second year, that's it. So it depends on transformer, how important it is, whether it is subjected to any external and internal effects, and also on the strategy of the network owner.
Right, Doctor. It seems that we have already taken some time from the second session, which already going to be presented by you.
Okay.
We have several additional questions that we'll sure try to provide an answer for at later stage. But just for the time scheduling, if you would please just move on to the next subject, and we'll back to the question later on.
This is, do you see my screen now?
Yes.
Okay, good. Well, the second topic is a different one. It will touch moisture in power transformers, how to estimate and what to do. And what I will try to cover is the effect of water in transformer, how it gets into that, how we can measure the moisture, how we interpret and what guidelines we may have and what we do about it. So actually, if we consider oil impregnated transformers, then water is considered to be the worst enemy of a transformer. So if it is low moisture in it, then we can consider transformer as a person in a good condition, and we can load transformer high loads without risk of failures, as well as person in good condition can work hard and not get into hospital. While wet transformer is opposite, it's like a person in a bad condition. We cannot load transformer, we must avoid hard loads to not to get bubbling in the transformer, and also the moisture itself inside the insulation increase the rate of aging of the transformer. And if we have a bad condition of the persons and he cannot run marathon, he will end in the hospital. So what the main point is that water or moisture and high temperature will sooner or later kill the transformer. So where we have a water, actually, the insulation of power transformer is based on mainly pressboard, paper, and oil. We have a lot of oil, like 60 tons in average in a large transformer, but oil has very low moisture content. When it is dry, then it is like 20 ppm, for example, which is very little compared to the amount of oil. Whereas in a cellulose, we can have quite a large amount with water inside. So what we have here is the conclusions that almost all water is inside the paper or in cellulose. The presence of water affects the performance of the transformer. The loading capability is impaired. We cannot load it as hard as we would like to due to decreased bubbling inception temperature. The dielectric strength also decreases if we have a moist paper and subsequently also moist oil. Also PD inception voltage will decrease if we have a presence of water. And of course, aging is one of the factors which also comes to play when we have a moisture and temperature. We just accelerate aging of the cellulose itself, which becomes brittle and disintegrates, and transformer eventually loses its mechanical strength along with dielectric strength. So this is something we want to avoid. Here I would like to illustrate like in graphical shape that we have a moisture content in the insulation here. So if we have a transformer which is new, with 0.5 moisture content and lower, so we can load it pretty hard at short time emergency limit. We can load like up to 200 degrees at hottest spot in the winding. And while it is 3%, then we should not go much above 100 degrees, which means we cannot load transformer as much as we would like to do. And if we know the moisture content and oil quality, we can also make a decision what to do with the transformer, whether it is okay to leave it as it is, even if it is more wet than we would like to. We can dry out or regenerate oil. We can, of course, replace it and put the transformer into less critical places in the network, or simply just scrap and put a new transformer, which is actually quite like last thing to do. So during the manufacturing, the cellulose insulation of transformer is dried out before it's impregnated, and eventually when it's new transformer, the moisture content is tried to be lowered as much as possible so that it's below 0.5% by weight. But as transformer gets older, the moisture content in it increases. If it is open bracing transformers, it will be like 0.2% a year, which is quite a lot. But most of the transformers are sealed, so there will be like 0.05% a year, which is not that much, but still several years coming, it will accumulate. And in old and deteriorated transformers, it could be like 3-4% more of water inside. And of course, it will all accelerate the natural aging plus effects of electrical field and temperature. So here it is also some graphs from IEEE papers showing that the aging factor of the kraft paper, for example, depending on its moisture content, is different. And if we have like 1%, we can run it very hard and go up to some aging factors of 30, 40 at very high temperatures, whereas if it is moist transformers, then these temperatures already would be intolerable for given moist transformer. And also the life expectancy at the same temperature, for example, 19 degrees. If we have 2% of moisture, we may have, or 3%, then we may have just 2 years. And if we have 1%, then we can have 12 years. So it is quite a difference here. So where the water does come from, how it gets into transformer. Mainly it is due to leaking gaskets, faulty water traps, like open holes where the water can get inside, like regularly when it is raining or it is high humidity in the air. Another reason is when you expose a transformer winding to humid air during installation of bushings or installation of transformer itself. as well as if you open it during the maintenance. So these are like factors to be taken into account. And also, even if transformer is not opened, the normal aging of cellulose will still produce water nevertheless. So that is anything which can be avoided. And of course, if transformer is insufficiently dried at manufacturing, that will result in higher moisture content from the very beginning. So here I have written like 1% and less than 1% for new transformers. But normally transformer manufacturers aim for lower than that, like 0.5. So how do we interpret different moisture contents, and how can we classify transformers according to that? And several standards are indicating that a good and new transformer is like still below 1%, whereas new and well-dried transformer is like half of it, like 0.5%. But everything below 1% is considered to be good and new. Then IEEE have different assessment. It says dry, it is here, all the way up to 2% from the beginning. But then actually the classification maybe is quite similar. So we have moderately wet about 2% up to 3.5 or something for IEC, and wet is in IEEE case starting from 2%, as well as SIGRE says that it is wet already, whereas IEC says wet is 3.5. And the last column is like Megger guide, so to speak, saying good new is up to 1%, dry is up to 2%, 2 to 3 is moderately wet, and everything above 3% is wet transformer. So this is guides which we have implemented in our HYDAX software, which measures the moisture in the transformer. So in practice, and it is very difficult actually what moisture contents we should allow, which not. It also depends on what transformer performs or functions in the network, whether it is critical transformer, it's huge transformer, or it's just a distribution transformer for some I don't know, remote location where people don't live, and maybe just in the summertime. So continuing, what methods we have for estimations of moisture in cellulose? Most widespread and best method is, of course, a direct method. So you use sort of Karl-Fischer titration or similar to take a sample from transformer and directly measure the moisture content. Then there are a number of indirect methods, like measuring moisture in oil in absolute values and relative saturation. We can do the power frequency times delta power factor measurements, and of course we can do a dielectric response measurements. Depending on what the instrument is available, we can use DC methods and or AC methods. Talking about direct method and Karl-Fischer titration on paper samples, which are described in SIGRE brochure. So it is possible only if you open the transformer, if you go inside and grab a sample. And also it is very difficult to get a representative sample from the transformer, since various locations may have a different water contents. Like here in the transformer, there were different samples taken from places on top of transformer, on the bottom, from the press board, from the windings, and you see there is a range from like 0.9% to 4.5%, and it also depends where you get the samples. So it is rather impractical to be used in the field as a diagnostic method. And also the laboratories which do this sample processing and measuring the moisture may have a quite widespread ranges, starting like from 1% to 2% for the same sample. And here we also have like from 2% to 3.5% from other sample. And these are different laboratories just taking the same sample of the paper and then analyzing it. So also absolute moisture in oil method can be used as a sort of criteria of getting to know what is the moisture content in the paper. But here are also quite a number of things to be concerned about, like how do you sample and how do you transport. Also the variation between laboratory results, and also that when you use the different diagrams for estimating paper moisture from oil, then you have to be sure that this is happening at equilibrium conditions, which is very rarely if you just sample oil from a transformer which has just been switched off and just slowly cooling down. There is no equilibrium in this case. And also standard diagrams do not cover aged oil and aged cellulose that may have different solubilities. So there are different ways to measure, but this method, water in oil, tends to pretty much overestimate moisture in solid insulation. And here are like examples, again, which large variations in the moisture in oil in ppm. It could be 3.5, 12%, or it could be like 32 or even 340. I don't know, it's measuring error or something, but we have quite a huge variation in these results as well, which when we go and then use the table for estimating the paper moisture, and depending on if we have 20 ppm or 90, we will have a very much different results. And also there is one thing more to mention. If moisture content is estimated from oil samples, that if sample is taken at 20 degrees, for example, then there is very little moisture in the oil, and small error can, like for example here, error of 50% or 3 ppm may lead to estimation of water content in cellulose from 1% to 4%, which is like going from dry to wet transformer, which is again not very good for decision making. Then we have tangents delta power factor measurements, which also are related to different moisture contents, of course. The higher moisture content, the higher power factor will be your tangents delta. And what has how you do this? You measure at actual temperature, you convert to reference temperature, and then you compare with guidelines. And regarding the guidelines, then tangents delta below 0.5% at 20 degrees is fine according to IEEE. And according to IEEE, if it is below 1%, it may be okay for service age transformer. And Adobe says that if it is below 0.3, then it is very dry transformer. And this is what you would expect for factory, the transformer from the factory. So this procedure is again normally done whenever you do the diagnostic tests, and it's easy, but it's affected by the errors due to temperature correction tables, which are not accurate for, let's say, you cannot use same table for new transformer and age transformers. They will be different. And typical measurement temperatures like 20-30 degrees and moisture and paper at power factor measurement and power frequency will have quite a low influence actually. And also it's not possible to tell if, for example, if increased tangents delta is related to high moisture content in paper or high oil conductivity, which also can happen. Okay, this I will skip. And dielectric response measurements. This is a area which we are working with, and mainly not DC methods, which is time domain, polarization, depolarization currents, but AC method in frequency domain. And we use frequency response measurement, which is capacitance and dissipation factor measurement versus frequency. So there are several weaknesses and strengths for each method, but AC methods seem to have more strengths and weaknesses. It's less sensitive against interference. Just one weakness, it takes some time, longer than time domain, for example, but in practical applications, I would not say it may have a critical impact on which method you choose. So electric frequency response measurement is quite similar to SFRI. We also have a generator and we have a reference voltage measurement, and then we measure current, and then we obtain the impedance of the test object, from which we can derive tangents delta and capacitance, which we then can plot as a curve in a frequency scale. And this is a curve which we analyze and which we use for moisture estimation in power transformers. And when we started to analyze all this technology, the method, and then what is influencing what, then this picture shows us where we have a moisture influence. It is at high frequencies here, and it is at low frequencies. But then there is an oil conductivity influence at a very large range of the curve, so to speak. And also we have geometry influence in the transformer. And of course we have a temperature influence. If we have a high temperature, then the curve would move towards right side. If we have a lower temperature, then it will go to the left side. And effects of moisture is in both ends. This end goes up and down depending on moisture content, as well as this end goes up and down, and oil conductivity will influence the curve shape in the middle. The lower conductivity will make curve go like this, and the higher conductivity would make curve go like this, and then make some dips and stuff. So in order to assess moisture by using the dielectric frequency response, we measure tangents delta from 1 kilohertz to 1 millihertz. Well, we can do it at 20 degrees if it is done at different temperatures. Then there is a temperature correction, not using tables, but using like a measured data to correct with the 20 degrees. Then in the IDEX software, we analyze this measurement, and it will give us the results as in terms of moisture in solid insulation, conductivity, tangents delta of the oil, and also power factor at measurement temperature and power factor at reference temperature. All this is based on insulation modeling in a transformer, which cannot be disregarded when you do these measurements. It is not like we can consider transformer as like a black box consisting of one material. It has still two materials involved, which has their own specific responses, which makes the curve shape changing depending on how the properties of two materials, what properties two materials have. And this is the model of transformer winding, where we have core, we have low voltage windings, then we have spacers and barriers and oil gaps, and then we have a high voltage winding around it. And it is maybe not that detailed showed here, but we can see the barriers and spacers hanging here, which is then reduced to big barrier, big spacer, and big gap of oil in order to make easier calculations of resulting model. And this is something what we have in the IDEX software, which is basically that what we have for us, our method for moisture assessment in transformers. So we do the measurement, we analyze the curve, and we get the moisture content here in terms of weight in percent. And we have also tangents delta at 20 degrees and oil conductivity to 25 degrees. So according to standards. And then we have also the Megger guidelines also here, showing that if you have a green moisture, then it means it's as new. And if it would be yellow, then it would be still dry. And then orange would be moderately wet and red would be wet. So this is a Megger way of measuring or assessing the moisture content in transformers. And in this slide, just would like to show what could be the advantages of using dielectric frequency response instead of, let's say, power factor measurement at 50 Hertz of power frequency. So since we have two materials involved in transformer, we could have a wet transformer with good oil, we could have dry transformer with bad oil, and we could have just a regular H transformer. And what issue here is that at power frequency, all of them would perhaps show the same value of the tangents delta, which is close to already high, no, not high, but close to values where you should start to pay attention. And if you start to pay attention, you would like to know what's going on, whether it is oil which is bad, or is it moist insulation, or it is just normal aging. Because depending on what it is, the different actions can be taken, whether you dry oil, or you like change oil, or you just dry transformer, or you just let it stay and then run further if it is not that critical that it can be overloaded too much to start the bubbling. Okay, this is also one of the tables where, like an example of maybe not really correct assessment of transformer conditions based on water in oil analysis. Like I mentioned, it tends to overestimate the moisture content in oil. And here were like 6 transformers which were scheduled for oil regeneration and hydration, since the water in oil data show that there is high moisture in insulation. And when doing the frequency response measurements on these transformers and making the modeling from IDAX software, it appears that only one transformer may need to be subjected to some overhaul or maintenance. The rest of them were pretty much all right. So this is just again, like an illustration that direct methods of oil samples may not give you like a correct answer. You have to be aware of it, simply as that. And also electric frequency response analysis is very non-invasive. You don't need to open anything. You cannot contaminate anything, and you can make a measurement today or tomorrow, different temperatures, see how results are. And basically, I would recommend it as a tool for moisture assessment, or a tool for transformer diagnostics. And besides all that, besides estimating of moisture content, we can have an estimation of dielectric properties of oil. We can see the temperature dependence and perform individual corrections so that it's more accurate than tables, and so on. And if we just summarize and conclude, what I have been telling is that moisture we want to avoid in power transformers. It will limit us in the loading capability of transformer. It will make age transformer faster, and electric strength will go down. And since water resides in the solid insulation, and DFR with IDAX is quite a great technique to assess this moisture content by doing tangents delta measurement at wide frequency range. Yeah, that would be all I was about to say. Now we have some time for questions.
Right. Thank you, Doctor, for this wonderful presentation. We have quite the questions actually.
Oh,
Some of them may be from the previous session, and
okay.
I believe some of them has been already been answered by other panelists. So start with this session. The first question asked is why does Megar use different interpretation from other established standards?
Like here. Well, if you look at the table, there is not that much difference. Like ISC and SIGRE are pretty much in line with Megert, so we have used this since these are more European based. And then we wanted to also have some distinction between like dry and wet, that there is something in between. But
Okay.
Hmm?
Another question we having is how to do temperature compensation in DFR test results.
How we do that? Can you repeat?
Yeah, the person asking how to do temperature compensation in DFR test results.
Well, the temperature compensation is already done automatically, and it is based on activation energy of the paper and activation energy of the oil. I believe that Diego mentioned it yesterday. That's the same Arrhenius relationship here. And we do that for our measurement, and this is what is critical, since dry transformer and wet transformer may have their own specific ways of to be corrected. So you cannot use the same tables, the same coefficients for wet and dry transformer. But to be concrete, it is Arrhenius relationship based on activation energies of paper and oil.
All right. Another question is asking why DFRA test is called DRANA test.
DRANA test. It is called DRANA test. So I understand.
Maybe it's
wrong. That is a very wrong
Yes,
way to call this
I'm
test.
against it. It's wrong. It's maybe because of, Omicron DRANA instrument is doing the same thing as we do. And when people in some region have been using DRANA all the time for this purpose, and they say it's like DRANA test. Like Megger is like making resistance of insulation. So,
I think this question has been already answered by Dennis, but it's been asked again. What is the best method for drying wetted transformers at site?
well, I'm not so specialist in this issues. But
If you want, I can take that question, Robert.
Yeah, you are probably more experienced with this one.
There's different ways that you can go on a dry out process in the field, right? And it depends on the ability and the equipment and many different things related even to the environmental conditions that you have on site. What is most effective for a dry out, considering that the unit is wet? Because if you just process the oil, that will take long time to dry from the solid insulation. So what you do is what we call the high vacuum and thermal process. So you apply vacuum and temperature to extract the moisture from the transformer. There's different methods, right? and there's another one based on heating the core based on low frequency signals to heat the core and then extract the moisture. But heating the oil, right? And there's a specific equipment in the field that will remove the oil, heat the oil. It will sprinkle hot oil on top of the core, and then by applying vacuum, right, the vacuum pumping will be extracting the moisture, and you will be controlling the moisture extraction. One of the ways that we are controlling that nowadays is using DFR technology with the IDAX unit. We are the only ones who can do that. And if somebody is interested in that processing, please leave us your contact information and we will explain that in more detail.
And please be also aware that if you have a moist transformer and the moisture is in a paper and it comes out very, very difficult. So changing oil will not do much.
Right. I have some questions from the chat, actually, not from the question and answer.
Okay.
So the question is whether the temperature correction is applied in the software while calculating the result for DFR testing, or it's based on historical trend data. Can you elaborate on that, Doctor?
No historical data are involved here. The whole temperature correction is based on activation energy of the paper and oil, and based on then they are combined in this model. You combine the paper, which is blue, you combine the oil, and depending on this ratio, depending on activation energies, you calculate the correction factors for shifting curves or calculating results at 50 Hertz or 60 Hertz.
Another thing I would like just to mention regarding this question is basically asking whether it's a historical trend data or it's a direct result coming directly with the test itself.
Well, it is like taken from direct measurement, which you do today.
All right.
Maybe,
another question.
Ali,
Yeah.
one thing with that regard, we have to differentiate power factor testing from DFR testing. Power factor may require some trending analysis to see what the degradation process has been. When you talk about DFR, it's an instantaneous characterization of the condition as found of the transformer. So what you see is what it is at that moment. So you don't need to do a trending analysis. Everything is you measure, you understand what's happening at that moment in that transformer, okay?
All right. Because that was on different chats and I tried to just combine them all together in one to deliver that question. Another question we're having is what are the acceptable limits of oil conductivity?
Well, I think for mineral oil, we have put some values of 1 picosiemens to 10 picosiemens is good. Above that. Now, when we go like this picture you see here, here we have some limits which we have put based on analysis from different standards. So below this value, it is low, but you can always change it. But I would say 1 picosiemens is fine, and then 10 picosiemens is good, and above that, then it is getting service stage and worse and worse.
Right. We have some other couple of questions, but unfortunately, we are also going inside the other the third session time. So if you would please just, Doctor, answer this question directly to them in the chat.
I will go to the chat. So now I stop sharing.
Our next session will be with Kenneth Petrov. talking about testing bushings at 1 hertz. Just to start afresh on that session, we will take a quick break of 5 minutes and we'll start at then. Ken, would you please just share the main page of your presentation and we'll start later.
I think I made Kenneth
Yes.
presenter.
So see you all in 5.
Okay, see you.
Thank you, Doctor. Thank you. All right. Welcome back, everyone. We will start with the next session presented by Ken Petrov. Would you please
morning,
open your
Ali.
mic? Hi. Good morning.
Good, good. So I assume you can hear me and you can see my screen?
Yeah, we can do that. Please feel free to start. And just one quick note before starting for the attendees. If you have any question, would you please just add them in a Q&A panel instead of the chat, so we can keep track of them even easier. Thank you.
Okay, thank you, Ali, for that message. Thank you, Roberts, for that great presentation on DFR and moisture just prior to this. And thank you to everyone for joining us here for our second day of presentations. I'm excited to be back to talk about a topic that I think a lot of you will surely find of interest. And it leans heavily on some of the information that Roberts had just discussed in his previous presentation. So I think it'll fit very well. So today I'm here to talk about the benefits of 1 Hertz power factor testing for insulation condition assessment. In particular, I'm just going to be focusing on bushings. We could also have another complete presentation based on transformers, but today will just be the bushing side of things. And we'll just jump right into, why do we want to test power factor at 1 Hertz? The traditional power factor that we're doing is taking a winding, let's say we have a transformer that's 69 kV to 12.47. We are then going to short the windings together, apply some voltage to the primary winding, and then measure some current that comes out on the other side. I know this is for a transformer, but the same concept applies to testing a bushing, except that total current is actually broken into a few different sections, one being the leakage current, the other being the capacitive current, and everybody has seen this sort of vector diagram here, and this is what we use to calculate either power factor or tan delta. The line frequency power test, is typically performed at 60 or 50 Hertz, depending on where you're at in the world. And then you must evaluate at 20 degrees C and correct with tables to limits set by standards. But if you had a keen eye and you saw in Robert's presentation earlier, is that when you are correcting with tables, the standards actually tell you that the values that you're using for correction do not apply to every single asset. So the standards are telling you that to get the best 20 degrees C evaluation, you must use a different method. The table correction factor method will not provide you with accurate, repeatable results. We'll get into more on that later. So what can you do after you correct if you are looking for a little bit more information on the changes in the asset? Well, you can trend those points in data over time. However, even if you have the data, and I would challenge a lot of people to see if they even have this historical data for reference. If you do happen to have it, the small changes that you may see in power factor are not conclusive to any drastic changes within the transformer at line frequency. There was also a part in Robert's presentation that alluded to that as well, that line frequency power factor is not sensitive to early and advanced changes in moisture and liquid conductivity. Furthermore, when the readings are not as expected, there's a lot of doubt that's introduced. And as I just mentioned, that early deterioration is not noticeable. And then this is where 1 Hertz comes in. There's a higher sensitivity to these early changes. So 1 Hertz can allow you to validate your expected line frequency results, confirm your questionable line frequency measurements, and then then finally detect problems when line frequency looks acceptable. This one here, Roberts had a fairly nice graph that he showed where in one example, the line frequency measurements all matched up, but the moisture in the 3 different assets was completely different. And why is that? Well, if we again look at this transformer with the press boards and the spacers, and we can derive this XY model, which again, Roberts was just showing. And from a very, very simplistic point of view, as you change the frequency, the response throughout the system will also change. And when you test at higher frequencies, such as line frequency, you have a relatively uniform response from the insulation system. But if you drop the frequency, the field is less uniform, so you are able to take a peek at different parts of the insulation system that you wouldn't be able to see when you're only testing at 1 frequency. So this is why testing at 1 Hertz provides different information than what you would see when testing at 60 Hertz. And what this all drives down to is that you have different confidence levels, different feelings about your asset and its reliability based on which testing you perform. If you do line frequency, that is good. You get good confidence because at least you have some information about your standard. About your asset, and you can evaluate those based on the standard. And this is typically the required 10 kV test that you do. To get better confidence, you can trend line frequency power factor over time. But again, I would challenge those in attendance to say that they have good power factor measurement history. They could always trend everything. It's not necessarily the case. So what you can do, the best thing that you can do is use a piece of power factor test equipment that can test at 10 kV line frequency and also test at 1 Hertz, using those same connections, using the same test form, and only adding 1 minute of additional test time. And most importantly, it gives you an immediate assessment of your insulation without the need for trending. In addition, what we can have now is calculation of what is called the ITC, or the individual temperature correction factor. This is the only way that an asset can be corrected back to 20 degrees C, and it pertains to only that particular asset. This ITC applies to line frequency, and it also applies to 1 Hertz. If you look in the standards, if you look anywhere else, there are no table correction factors for 1 Hertz, but the 1 Hertz must be corrected back to 20 degrees C in order for proper evaluation. And how can you do that? The only way is going to be ITC. In addition to the 1 Hertz, you may have also heard the term narrowband DFR. It's just a little bit of an expanded range from 1 to 500 Hertz, where you can get some additional information. But if you really want to know the exact state of the insulation that you're testing, you must do a DFR IDAX test. This is the only one that's going to give you that conclusive solid or liquid insulation condition assessment. But if you don't have the IDAX and you are doing line frequency power factor today, how can you improve your evaluation? That will be testing at 1 Hertz. And now I have a few examples of exactly how testing at 1 Hertz helps you confirm good measurements, validate questionable measurements, and then finally detect deteriorating insulation when line frequency power factor looks good. So the first example that I'm going to give is going to be for a 1978 transformer with 115 kV bushings tested at 11.5 degrees C. And when we look at this result, we see that the H bushings, their line frequency power factor values are high, but there is no deviation from the nameplate in terms of capacitance or percent power factor. So we really have no concerns about these particular bushings. But again, if we only had line frequency power factor, we may not be able to be so confident in this assessment, and for reasons you will see later on. But when we look at the 1 Hertz for this particular set of bushings, we can see that the values obtained are all relatively low themselves, and so there is no cause for concern. If you remember those graphs that Roberts was showing, for the assets that had high moisture or high oil conductivity, you saw the graph tend to trend upwards pretty steeply after 10 Hertz and go up at 1 Hertz. And that is how we are knowing if this 1 Hertz value is acceptable or not. So some conclusions for this transformer is that 1 Hertz validates the expected line frequency measurements. Moving on, we are able to tell when a transformer allows us to validate when bushings are questionable or not. Here we see that we had another set of high side bushings tested at line frequency. These look within the acceptable limits ranged for an aged bushing. There's a small deviation from the nameplate in terms of power factor, but again, nothing too severe when only looking at line frequency and using the temperature correction tables. However, when we look at the 1 Hertz, we see that there is an elevated value for H2, which looks very much different than its sister bushings. And this elevated value then confirms the elevated value seen at line frequency power factor. But if we take it one step further, we can use the ITC, and we now see that the H2 bushing is deviating quite a bit more from nameplate than when we use those outdated temperature correction tables. And looking at 1 Hertz, when we correct back to 20 degrees C, the change is now much more drastic, 7 times measured versus 15 times different for this bushing here that has gone bad. So this is a further confirmation of those poor line frequency measurements. But again, all we're doing with the 1 Hertz is pointing you in to look at a particular bushing that may have a problem compared to its sister bushings. But the 1 Hertz cannot tell you the exact state of that particular bushing or asset. So what you need to do is bring out the IDAX, and this will give you the definitive answer. And for this particular customer, when they brought out the IDAX, when they tested the H1 bushing, they saw that the moisture was low and was within a good range. But that H2 was showing service aged, moderately wet, and almost approaching very wet. So again, the 1 Hertz will not tell you what is wrong or where the problem lies within your particular asset, but it can direct you where to focus your additional maintenance and test efforts, which is really what we're all trying to do in the world today. We have less time to perform testing, and we need to see how to better focus our energy, and that 1 Hertz power factor testing gives you that capability. So again, looking at the 1 Hertz, this confirms early and advanced degradation of insulation. We have improved the lifespan of this 50-year-old transformer by identifying a problem bushing and giving the customer the ability to take action and rectify that. And with 1 Hertz, even if you don't use correction factors, you can just look for the difference from the sister assets. And this is perhaps the easiest way of thinking when looking at bushings is just compare the values from their sister bushings, and most of the time you can notice differences early on when looking at 1 Hertz. But now I want to move on to looking at bushings and detecting problems when line frequency looks acceptable. This will be the same example from the transformer that I just discussed earlier, where confirming that 1 Hertz can show that a bushing is in good condition. So on this same transformer, this customer performed the line frequency and 1 Hertz testing on the high side and also on the low side bushings. If we look at the low side bushings, corrected with table correction factors, everything looks great. There's only very minor deviations from nameplate. So without any additional information, a customer such as yourself or the one in this study would say, all of these bushings are in excellent condition. We can put them back into service without any expected problems to come from them. But if we look at 1 Hertz, we can see that the X3 bushing here is showing quite a bit of a difference from its sister bushings. And again, at this point, we don't even need ITC, but we will go through that. But when you are looking at a sister asset that was built in the same year, that is operating at the same voltage, that was built by the same manufacturer, presumably out of the same batch, and it's been running in the same environmental condition as the other sister assets or other bushings, if a value starts to change, then you can be pretty confident that there is a change occurring with that single bushing. So now if we look at ITC, we can see that the line frequency value is now showing investigate, where it's having a major deviation from the nameplate. And the 1 Hertz is now showing an 11 times difference than its sister bushings when properly corrected to 20 degrees C. So the conclusions from this one here is that service-aged insulation can appear within limits. We just saw that when we look at the X3 bushings, if we were only using temperature correction tables, we would have never been able to identify this change in a bushing, which it was obvious that it had changed when you started looking at 1 Hertz. We also seen that the temperature correction tables are not accurate. For this one particular bushing, it did not age as expected compared to its sister bushings. So the temperature correction tables are completely out the window and are not appropriate for evaluating this set of bushings or any asset, and that is directly coming from the standard. Finally, the analysis at 1 Hertz provides additional information, and this is additional information using the same power factor test set that you are using to do the 10 kV line frequency result. And when you do the testing at 1 Hertz, you can detect early and advanced degradation of insulation, which you can then use to improve your maintenance strategy. Again, we're not saying to go and test IDAX on everything, although that would be my suggestion for pretty much everybody doing insulation evaluation. Is I would always do the IDAX because it can tell you conclusively where you are having problems. Or you could use the IDAX in this way, where you test at line frequency and at 1 Hertz to then further improve your maintenance strategy. Because at the end of the day, if you see an elevated value at 1 Hertz, you're going to have to bring out the IDAX anyways in order to get that conclusive insulation analysis. What Megger has done with the Delta 4000 and the Trax Plus TDX is give you additional information beyond line frequency power factor using the same test set and same test connections. And when you look at 1 Hertz, we can tell you where best to focus your energy moving forward. So some overall conclusions here. The 10 kV line frequency power factor, bottom line, it is insensitive to developing changes in insulation. You saw a perfect example here today where line frequency power factor can look good, but the 1 hertz will look bad and there is a problem with an asset. And if you remember from Robert's presentation with the graph earlier, where he had the 3 plots, he showed definitively that 3 assets can be tested, show similar line frequency results, but then have varying levels of moisture in the transformer. Next, temperature correction tables do not consider the unique operation or aging of the asset, and this leads to inaccurate correction of line frequency results. In addition, temperature correction tables only exist for line frequency. So if you are going to try and correct frequencies other than line frequency, the standards have no solution and you must use ITC. The trending of line frequency at power factor at 20 degrees C, this one, the results are not always available. It's just not going to be something that will be readily available all of the time, and they are calculated, these 20 degrees C values are calculated using inaccurate temperature correction tables. So my question for everybody would be, why would you want to continue to evaluate and compare historical results that were corrected in an inaccurate way? It just does not give you the best information possible. So finally, what some people can do is compare line frequency power factor to a proprietary database, but unfortunately these have high membership costs. They're not readily available, and since they have been using 20 degrees C to do all their corrections, again, it is going to be inaccurate and not very suitable for getting the best insulation assessment that you can get. And that's where 1 hertz power factor comes in. Using the same connection as your line frequency power factor test and only 1 minute of additional test time, you can get more information about your asset. And what we've done in PowerDB is that we now automatically test at 1 hertz without any additional configuration needing to be done by the end user. So you open up the form, you select the asset that you're testing, and we are going to test it in the best way to give you the most complete information about the asset possible. When we do this at 1 hertz, we are able to give you an immediate assessment at any temperature without any trending required. We can use this information to validate expected line frequency measurements, compare questionable line frequency results, and most importantly, detect early signs of insulation changes when line frequency looks acceptable. So when you have one of these test sets that will test 1 hertz at 250 volts, you can implement this 3-step insulation evaluation method. The first is going to be high voltage line frequency power factor. Of course, this is your 10 kV, your 50-60 hertz corrected to 20 degrees C, and it's required by standards. So we know that you're not going to stop doing that today. And that is why we want to introduce the 1 hertz, because again, it's using that same connection that you're already required to use today. And then we're just going to run one additional test that takes less than 1 minute at 250 volts, and then correct that 1 hertz value to 20 degrees C. This will point you in the direction that you can do further investigation if needed, like in the examples. We did not have to run full spectrum definitive DFR on every single bushing. We only had to do it on 1 or 2, 1 to confirm what the good measurement was, and 2 to confirm when there was a bad 1 hertz value measurement, and to see what is the problem with that particular asset. And Megger has a couple solutions for doing this. The first is the Delta 4000. This is going to be your standalone 10 kV or 12 kV installation diagnostic system. We can test from 1 to 500 hertz. You have probably heard us talk about narrowband DFR in the past. This is one step up from 1 hertz diagnostic, but it is there and available for those power users. We can provide accurate measurements in any type of substation or generator, so that way you have the most reliable accuracy possible. The built-in patented individual temperature correction that I was talking about, this temperature correction is required for evaluating 1 hertz properly, and is the only method that should be used for line frequency power factor correction, since the tables state that, or the standards state that the tables are inaccurate and should not be used. The Delta comes in a lightweight 2-piece design, and we have also released some new accessories for the Delta, which will allow you to perform ratio testing on CCVTs. Next, there is the Trax plus TDX. This is the multi-function solution for transformer and substation testing. This gives you the same functionality as the Delta, but adds in winding resistance and demag, turns ratio, leakage reactance, excitation current, and then further gives you the ability to test instrument transformers, circuit breakers, and contact resistance. And with that, that brings me to the end of my presentation, and I look forward to answering your questions now.
All right. Thank you, Ken. We have some questions, starting with first question, whether LF, I believe he means line frequency, or 1 hertz test can detect the bushing insulation degradation due to any electrical stress, but not due to moisture contamination.
So when we look at 1 hertz, we are not able to tell the exact change that has happened. We just know that there is a change that took place, and you will need to do an IDAX in order to determine the moisture and the oil conductivity. I would assume that if there's an electrical stress, and perhaps Diego can comment on this, if there was an electrical stress that did not change the moisture or the oil conductivity, I would expect the capacitance to change. And I don't think that 1 hertz would provide any additional information. I think the capacitance might be enough there. Would you agree with that, Diego?
Okay, so one of the things that is important to highlight here is that when we're talking about bushings and the 1 hertz, it's basically the analysis of the condition of the bushing corrected properly to 20 degrees C, right? And this is a numerical value, right, that we have investigated. And, you know, if we talk about high voltage bushing, we say if it exceeds 1% at 1 hertz at 20 degrees C, then there might be an issue with this bushing. Now, the other thing is that what we have found mainly in high voltage bushings has not been usually issues with moisture, has been issues with contamination and degradation of the solid insulation due to overheating, due to transients in the system that have affected the insulation condition, due to faults in the system that have affected the insulation condition. So let's keep this in mind. Assessment of moisture per se is one of the properties of DFR, but with 1 hertz, we do see the sensitivity at 1 hertz of the deviation of this dielectric response. So looking at this number, right, even it's a trigger, it's a warning point. If it exceeds 1%, for example, on high voltage bushings, it's telling you it's about time to do further investigation. Don't just rely on the condition of the bushing to continue the operation, or schedule something in addition to that. That will be the full DFR test, of course. But again, don't think about moisture just as a typical issue on bushings. It could be mainly degradation or contamination of the insulation in the bushing. Okay.
All right. Another question we are having is, what can cause degradation of bushings?
I mean, moisture ingress, electrical overstress, as Diego just mentioned. There's a multitude of things that can cause bushing degradation. Poor manufacturing quality, leading to differences in, differences in the sister bushings. Poor termination within the transformer itself. There poor transportation of the bushings, from the manufacturer to the end site. I have another case study that I didn't show here, but it was RIP bushings. 9 were delivered. A handful had water inside the wooden crate and within the plastic, and 1 Hertz was used to confirm, that there was moisture ingress into these bushings. So there are many reasons why a bushing would degrade, all the way from manufacturing through just normal service aged degradation.
Another question asking, what is the acceptable standard for dry type transformer tan delta test?
Well, we were talking about bushings today, but for dry type transformers, it does not have the liquid inside, so the 1 Hertz power factor values are going to be a little bit higher. But it's, I don't have that specific answer today. But it is helpful to look at sister assets, sister dry type transformers. But if you're only looking at line frequency, then everything that I've presented today holds true for that. It's not going to be enough information to make an accurate assessment of that particular transformer. You're going to want to drop your frequency down to 1 Hertz and look for any elevated values, especially compared to your sister assets.
One of the things to talk about dry type transformers is which kind of dry type, right? It might be an encapsulated type, it might be high temperature, dry insulation, Nomex insulation, paper insulation. There's a variety of types of dry type transformers that are being used in different applications. And your power factor might go from 0.5% all the way up to probably 3%, and there might not be anything specifically wrong with that transformer. So there's a couple of things that are discussed when you try to analyze a dry type transformer. One of the things is, for example, to work on a TPAP test. Okay, so you can perform a TPAP test. You can perform variable frequency as well, looking into the narrow band between 1 Hertz and 500 Hertz. But again, you cannot just compare the two transformers in this case, because the condition of, and what is exposed this transformer to, right? There might be some dust, there might be some humidity that it's in touch with this specific transformer. So first you need to identify what kind of dry type transformer we're talking about. Is this an encapsulated? Is it Nomex? Is it paper? Before you do any kind of assessment on power factor conditions.
Is it okay if I also talk a bit about this? Ole Bensler, I spoke yesterday as a presenter. And also for the dry types, sometimes they're like shielded between primary and secondary side. So then you would focus more on the ground measurement, because the UST measurement, you will only see the shielding between the 2 windings. And it's also important to point out that the Tangens delta, for example, of this type of power transformer might change a bit with time, because the the core gets more put into its structure over time, so to say. That when you do it after the factory, it hasn't been fully, I don't know the correct word, but it hasn't been fully solid yet, so to say. So as time goes on, the value will change a bit. So I don't think it's normally you perform the partial discharge test for these types of transformers to look in cracks in the insulation.
All right. Another question asking, what would be the remedies if 1 Hertz test values are bad, or any other specific test is recommended to know the condition of insulation?
So with 1 Hertz, we are giving you the opportunity to determine what next steps to take. If you have low power or low 1 frequency results, then there is no additional steps that need to be taken. If you have, let me go back to this here. If you have high 1 Hertz results, well, then it's up to you to relay that to your customer, whether that is your parent company or somebody that you're doing these services for, and you need to recommend to them that additional action needs to be taken. And that additional action could be a scheduled maintenance in 6 to 12 months down the road, or it could be an immediate replacement of that bushing. It depends on the criticality of the asset that we're talking about. But let's say that you found this problem with this bushing here, but the customer does not have an extra 115 kV bushing laying around in order to install. Well, it's better that they know now that they have to order that bushing than if they were to just continue on as if everything was perfect and then all of a sudden had a bushing fail. Now what are they to do? Now they may not have 6 months to wait around for a bushing, so they have to scramble, get a different temporary substation in. Who knows? So what is the next action that you take when you have bad 1 Hertz? Well, it really depends on what the customer is expecting from this particular asset and what they have available to them. Do they have an IDAX on site? Well, that'd be great. Then I would do an IDAX 100% for sure if you have a bad or high 1 Hertz power factor, because it will tell you exactly what's wrong with it, and it will tell you how bad it is. So that way you can then further plan and say, okay, we need to replace this bushing, but we can do it within 6 months or a year. But again, you may not have the IDAX. It may just be a small planned outage for a day. You may not have the time to do this additional testing. But if you have the 1 Hertz, you can then have the power to know and better plan for what your next testing or next actions would be for that particular asset.
All right. For the last question before going on another break, someone is asking for an open secondary of a DY1 vector group transformer that having the rating of 33 to 66 kV. How much voltage can be produced if star point is not earthed?
So are we talking about?
I'm sorry, but I believe he recorrected the question, asking for a voltage for a ratio of 33 kV to 6.6 kV instead of 66 kV.
So we're talking about during a power factor test, yes?
He did not specify, so I
Well, I'm
assume
assuming
line frequency.
since we're here talking about line or power factor testing, if I go back to this slide here, when you short these together, you're not enabling the transformer to work anymore. So you really and I think Diego will need to comment, you shouldn't have voltage on that other side. And further, if I'm bringing up in the delta right now, that if you have a YN, I don't think those need to be shorted together anyways. Just give me 1 second here so I can bring up my connection diagram.
I'm not quite clear on the question. He says how to test bushings for a 33 to 6.6 kV transformer. First thing, the question is, typically you will have a test tab if you have a bushing that is 69 kV and above. There are bushings, yes, with a test tab where you can test the capacitance C1 or C2 right below 69 kV. So the first question to me will be, your 33 kV bushing has or not a test tab? On your low voltage side, the 6.6 kV bushings certainly don't have a test tab. So the only thing that you can do probably is a hot color test, right, on those, or if you want to do an insulation resistance test, that will be what you can do on those. And for the 33 kV, again, if it has a test tab and you can test by power factor C1 and C2, that's what you can do, right? And that's the test that you will do. And if you find your line frequency power factor, your 1 Hertz, to give you the indication that additional testing has to be done, then you will apply a DFR test. If you do not have a test tab, then the only thing that you can do is a hot color test.
Yeah, and I guess perhaps if we look at this PowerDB form, if I put in the voltages as we discussed, 33,000 to 6,600 volts. If we look at the test voltage that we want to apply in a particular bushing, we don't want to exceed the rating of that bushing. So perhaps he means 10 kV on the primary bushing and 3 kV on the secondary bushing. But yeah, I would like some additional information or to be able to have an email back and forth with this particular customer so we can more accurately answer his question.
All right. It seems we're out of questions for now and a little bit behind on our schedule for that time. We'll take another, I would say, 5-minute breaks and then start fresh again with Dennis on power transformer testing bands. So we'll see you in 5 minutes. All right. I believe we can start now again, everyone. So Dennis, please feel free to start your presentation.
Thank you, Ali. Good morning, everybody. Ali, can you say if you can see my slide, if you can hear
Yes,
me?
we
And
can
you see
see
the
your slide and hear you very clearly.
Very good. Okay, so I have an opportunity to present the last presentation in today's series. And as the title already says, we will be discussing a comprehensive condition assessment of a power transformer with an integrated test van. As the picture already shows you, we will be talking vehicle, automobile that has a collection of instruments, basically all topics that you heard of in the last 2 days are collected together and not just transported, but also integrated in the overall system. So to start introducing to the topic, transformer is an expensive asset in any substation, and its condition and quality should be checked. Most checks are organized under factory conditions when the transformer is produced. So depending on the geographical area, you see a number of standards that define this testing, and testing is done to assess the condition. And if you look at a later stage of a transformer life, you will be operating this asset for a number of years, let's say 10, 20, 30 years. And during this operation process, there are also guides like a SIGRE brochure 445 that tells you what kind of tests you're supposed to organize during the maintenance process on your assets. So let's have a look at this brochure and at the one particular table that tells you what does it mean to assess the condition of a transformer. So transformer might have different problems, starting with magnetic circle, with electrical, so windings, bushings, tap changer, contact problems. Inside the winding, that could be interturn shorts or opens. So all of that must be diagnosed and found to assess the condition properly. And there is not one single method that will provide you answer for any question. There is a number of them. So therefore, we're talking an integration of those methods to make a system. So at the very bottom, this is a very, very informational and powerful system where you take a sample of your insulating fluid from the tank and send it to the chemical analysis to check the dissolved gases. It can help you find a lot of problems already, but it definitely does not cover all. So if your attention was triggered by the suspicious DGA results, you can schedule an outage of this transformer and plan some tests. And the tests can be grouped under basics or advanced tests. Within basics, you're simply rechecking the design, the geometry parameters that are set by the manufacturer, by the designer. And you always have a comparison. What was before, what was in the commissioning phase. You can always open those reports and compare. In the advanced testing, you are looking for all type of frequency responses, like Ken, Diego mentioned previously. The transformer usually does not see those frequencies, but those frequencies are very useful to see the material worsening or geometrical change in the structure of the transformer and see it at a very early stage before the problem became very critical. And PD, as the abbreviation is definitely well known to you, is a partial discharge, is also a very early symptom, a phenomena that tells you that there is a there is a process that takes place inside the tank, and it might breach the complete insulation and lead from a partial to a total discharge or breakdown. So this is a very useful to detect in an early stage, to localize, and maybe even to fix it. So the condition assessment means to look at all of these properties, to structure them well, and derive some conclusions from all those findings. So that was an example of a SIGRE view. The next slide shows you a slightly different view given by the IEEE that shows again the structure of the transformer and the fact that every piece of the transformer is supposed to see different tests to identify different problems. And corresponding to that, you see a portfolio of Megger, and you see that traditionally there are products designed for just a single purpose, a single function. And there are products that cover many aspects. And of course, there is a multifunction approach, product trucks that you've seen the last 2 days that tries to make multiple tests and connect from out of the single box. And of course, there's an ultimate flexibility if you have a dedicated vehicle that you can mix and match, collect all this portfolio together and run it as a integrated system. So what are the problems that you see in field? You have to do, not a single test can answer all questions, so you need to work with different test sets. Even if you're talking about a multifunction test set, that platform also works with the main unit plus a number of accessories. So you always need to interconnect those and prepare a lot of circuits to check all these test parameters. In certain areas, we also have a very harsh climatic environment. So it can be, so you would want to protect the personnel and the sensitive electronic equipment from the climate conditions, whether it's extreme heat or cold or sand or any other regional problems. If you work with this standalone equipment, you always have a bag with long cables that are going up to the high voltage bushings, and you need to spend time untangling them, putting them back to the bag, and so on. So that is an issue. Statistics show that a lot of accidents in the substation environment occurs just by the fact that a test personnel must climb up and down the ladder on the cover of the transformer many times to interconnect different test circuits, make a short, make an open test, make the bushing test. You always need to rewire your leads repeatedly. So when do you perform tests on your transformer? Typically in the very beginning of the lifetime, at the stage of commissioning, when the new transformer arrived to your substation, you are doing the check. When you run the transformer for many years, it's a good practice to make periodic checks, like every 4 to 5 years. You stop the operation and schedule comprehensive testing. This is done to prevent an outage in the future. In case if still an outage took place, you need an electric toolbox to localize the problem, to troubleshoot and to figure out what component is affected and how to fix it. Whether you scheduled an outage and or experienced an outage and even conducted a repair on site, or even needed to send the unit back to factory, you must make an after repairman check to see if all the wiring been done properly before you energize the equipment again. So If we coming back, that was the introduction part. If we coming back to the collection of test methods that can be interconnected together, you see the transformer in the middle and a number of tests. Most of them have been already addressed in the previous lectures. You see that they all can be accommodated inside on board of the vehicle. Let's look at this typical test van, and we open the sliding door from the side, and we look at the operator compartment. So you see here a chair. The environment will be climatically controlled with air conditioner, and operator can close doors and work in the near office like environment. So you see here modules that are responsible for the power supply, selecting of the instruments, monitoring the safety conditions and contacts, and of course the central computer that will be running the test, running the equipment and instrumentation on board, and collecting all information to reports, and making also forming a database and allowing you to compare the tests over several years, or comparing it to the sister units or different substations. Of course, some little stuff like keyboard, mouse, and all the equipment that you will be operating is arranged here under the table. Let's have a closer look. You see here two different pictures where a single function instruments are integrated together, and the multifunction instrument tracks is also integrated together. So you see, if you possess this equipment, if you know how it looks, you can easily recognize that there are instruments Delta, MTO, IDAX, S1 on this side, and the similar look on the other side. In the back of the vehicle, all cables are collected on cable reels. They are typically available in two lengths, 50 meter for power supply and protective ground. This is the drums 5 and 6, and measurement leads that are normally 30 meters. They are there for high voltage cable up to 12 kilovolt, red and blue lead, interlock lead, lead for the external safety lights, just to indicate the presence of voltage, also outside of the vehicle, to give a message or warning signal to the to a second colleague who would be working outside and connecting the leads, and low voltage test leads that are connected to both sides of the transformer at the same time. So all three phases plus neutral on H and X side. And the main piece of the equipment here is the switch box, basically something that allows you to share the same cable connection that you established between the test object and your van, and interconnect this cable to a different instruments on board. So the main idea is that we try to make a one-time connection for the HV tests and one-time connection for the LV tests. So you see here a van and a number of cables that go out of the van. First of all, of course, is the protective ground that connects the grounded tank of the equipment with the vehicle. We also use the second ground reference point, because that cable can be very long, 50 meter, and there could be potential differences between this remote ground and near ground, ground close to the chassis of the car. So the electronic circuit will always monitor the voltage difference between those two ground points and switch off the equipment if necessary. And then you're making the typical connections that are needed for HV test. HV test means insulation tests. So you short all three phases plus neutral together and connect your HV cable, red cable, So on high voltage side, on low voltage side, and if you happen to have a tertiary on your transformer, you even take a blue lead and also connect it to the tertiary at the same time. You observe the lights, whether it's safe or not safe to touch leads or interconnect. And you connect the other end of the drums or cable reels to the switch box. So as I said, one-time connection for HV tests. What kind of tests you can do with this one-time connection? Capacitance and tan delta, and output AC signals or AC voltages up to 12 kilovolt. You can conduct insulation resistance with guard up to 15 kilovolt DC. You've seen this abbreviation before. It's a narrowband DFR, very valuable 1 Hertz values that are done to assess the condition of bushings or windings. And you can bring the ultimate DFR full band or broadband technique, even with the amplifier up to 2 kilovolt, and conduct the full spectrum assessment from DC up to 10 kilohertz frequency to get the material properties and to establish moisture content in your cellulose and conductivity of oil. This is done with one connection, and then the switch box enables you to interconnection of these instruments automatic per mouse click inside the van. Same principle is organized on the low voltage side. Here we also strive for one-time connection. And here, this time, we remove the short and we connect each bushing with individual Kelvin clamp, 4 clamps on HV side and 4 clamps on LV side. And connected to the particular switch box and organize a TTR test that checks amplitude and phase angle, polarity, excitation current. We can connect a winding resistance meter, make a DMAG after this process is over, check the condition of a tap changer, record the dynamic oscillograms and compare them different taps, make a short circuit impedance. Of course, in that case, we will be removing the low voltage side, the clamps from the low voltage side, and making a very solid short between the phases ABC on the low, and making the 50 Hertz short circuit test or a frequency sweep for the short circuit conditions. And we can organize a power loss test at reduced voltage. I will cover that in a separate slide later. Some customers also require to have a high pot on board of the vehicle. And in that case, the vehicle gets slightly longer because we need to accommodate a single phase 100 kilovolt AC transformer, or let's say voltage source, that can output up to 20 kVA test power. And that test power can be outputted as a DC using the coax cable, or as an AC, so coated wire that would go directly to stress the HV side or LV side, while the other one is grounded. So typical application for the high pot is that you apply a 50 Hertz test stress for 1 minute, and you see if test passed. Basically, if you've seen no collapse of the voltage on terminals, it means that the test passed. Sometimes it is being, you can also connect a quadrupole and the PD test set and record also any PD emissions to see that not only that the voltage not collapsed, but also if there are any PD at the early stage already happening in this insulation. So a look from the practical substation, you see this vehicle, you see a little gas insulated bushing through the body of the vehicle, and then the straight connection to the, in this case, neutral connection on the high voltage transformer, where you can check for applied voltage test. Power loss test is again very popular in certain countries and given by the certain standards. In this case, we accommodate a special three-phase voltage source, so a variac that can regulate the output voltage from 0 to 400 volt or output current from 0 to 16 ampere, three-phase. And we can connect a watt meter in between and see what losses, or let's say what power is being consumed by a no load test or a load test on the transformer. It's important not to confuse it with a factory test, because in this test van, we are talking a compromise solution, a solution that only gives you 400 volts, which is maybe fine to test the distribution transformers that have the winding rated to 400 volts. In that case, you are close to rated conditions, but it's not okay to test transmission. Basically, it's not okay to try to compare it to the factory settings. But if you happen to have a manufacturer reference performed at reduced voltages, then it's a direct comparison. When the transformer was new in the factory, tested with 400 volts, you know what loss has been produced by the core or by the windings, and you can easily compare it to this reference. In the past, I always told the word van, but some customers might also prefer to have it in a trailer packaging, or even as a laboratory workbench, where you can put on the floor in the factory and make some tests, or not a factory, maybe a rewinding shop, where you can conduct all those typical routine tests. We can also provide you an integration of the already existing units that the customer possess and would like to integrate into this overall test system. Recently, we also made a mini solution. So a solution that only has one instrument on board, not the number of it. It means that it's a cheaper version, and it lacks all the switch boxes that we have on HV side and on LV side. But since the instrument is so multifaceted, multifunctional, it still can cover, let's say, 60% of all the tests that are needed to assess the condition of the transformer. So in this case, there will be, again, a very little control unit, very simple, that is also responsible for showing you all the problems around it, around safety circle. And you sit inside and you perform all tests from the office-like space environment. If we look at we were telling last 2 days transformer assessment, but especially service companies, they often go to a substation and see there not only transformers, but also CT, so current transformers, voltage transformers, circuit breakers. Sometimes same people are also testing battery discharge or protection relay systems. So as you can see on that very schematic slide, that the existing test van is already covering a big share of the substation. And if you take a few portable devices, you can easily cover the rest of your daily needs. And you can see this solution as a full-scale substation test van. Looking at the software, of course, I was telling you that everything has a central control, so you can activate a certain equipment directly from the main computer. For example, you activate IDAX, mega ohm meter, or multifunction instrument tracks. And at the next step, you go and move to the next software, to its own software that guides the testing, collects all the data to a report, and that report is ready to be copied in the overall database or exported to a different ERP system software or any Excel spreadsheet that can be used in the external analysis. So to conclude those slides, the transformer test van concept tries to combine routine tests and advanced diagnostic test techniques. It allows you a complete transformer check in field, and it helps you to reduce the time for testing and prevent any accident, because it helps you to interconnect the leads fully automatically. You will be collecting a lot of data, and on the data handling side, we will be forming a report, copying all the data electronically to a database, and providing you a comparison to previous tests. So that was on the slide, and I think slides are good, but even better would be to see some images. And Ali, can I ask you, do you see the moving picture?
Yes, we can
Okay.
see the video, but if there is any sound, it will
No,
not be
there
shared.
will be no sound. There will be me just speaking and trying to introduce you to the concept. So
Just
see,
give you a quick recommendation. If you would share the video file itself directly, it will show a better smoothness, I would say, to the
Right.
animation in the video, instead
I
of
think
sharing your screen.
in the I try to do it right now, but later I will also publish a link on the YouTube, and everyone can comfortably look at the video with the proper soundtrack and everything. So right now, from my side, just a short introduction. So you see the vehicle under 3.5 ton is driving to the particular test object, a transformer, and we look inside, we look outside, and we trying to interconnect it. So the table that you already seen in the past, and initially, of course, all the settings should be made. So in the back, you're taking some cables out and reading the diagram, how you're supposed to be connecting for LV side, for HV side. You're starting now with the protection ground. You connect it to the tank that is normally grounded in the substation. You establish auxiliary ground connection to the soil spike. You put an external lamp box to indicate any state when you have the voltage, and you go on top of the transformer and making the connections to the bushing. So first you remove all the ropes, make a short, and making the connections. So if you now look inside, you see that, like I was telling, it's a central computer, it's a control units, and there is a number of instruments under the table. And this is a fully project-based approach. We can integrate any instrument that you wish, and each instrument can be easily removed. That was also a very important design task. In case if the transformer is sitting in the building or not in the easily accessible location, you can take it out within a few seconds and operate on the standalone basis. So now we're removing the connection, grid connection to the transformer. We making the short where all three or four terminals in that case are interconnected. Same is happening to the low voltage side where the bus bars are removed on the LV side, and we making the short in this instance as well. And of course, we will be connecting now the test van. So HV lead is taken out and brought to the top and connected to the HV side. And the other end of the cable will be connected directly to the switch box. This is what you see. Now, depending how complex your transformer is, for the 2-winding transformer, you just need to connect a red lead on the LV side, and you are good to go. So you close doors, and you go and operate the software. Okay, so here's the power supply also shown. You connect it. We can provide a 3-phase power supply or single-phase power supply depending on the power ratings of this test van. So of course, since you working with reports, you need to set up all the data, temperature and nameplate related. You activate the software, activate the instruments, and you see that the light turns red. And the database and the control software will guide you where you do line by line, collecting the data and forming your reports for the condition assessment. So the example is showing you now tan delta testing, where you can do all pieces of insulation, high to tank, low to tank, and so on. And then the next step is you leave the cables as they are, and you simply go to and activate the DC source and collect the data for the insulation resistance. So in this case, you output 2.5 or 5 kilovolt. You see 5 kilovolt in this example. You wait for 60 seconds. You form the table. You calculate PI or DAR. And if you are reconnecting the leads, again, you are swapping the leads and making the second half of the report completed. So after you've done HV tests, all your tables are done for insulation resistance and for tan delta. Imagine you also done the bushing tests. You are continuing with LV. And here you remove the short and you connect each phase now individually with the Kelvin lead on HV and LV side. And you connect the other end of the cable reel to the switch box output. If you need to connect to the control of the tap changer, you also using the particular cable reel. You connect up and down connections and power supply, and you are ready for a remote control on the tap changer. So the software, or you can press the button by hands, can go through all taps and all phases. So this is an example shown for winding resistance, where you can see this is a test done at tap 19. And then when the report is formed, you can press the button, or the software can do the job for you, depending on what instrument is integrated. And you see the results are collected in tables and graphs. And finally, if you can, DMAC is being shown. And after you conducted the test, this is the ratio, where you can also go, again, all taps, all phases. Finally, you copy all data if you connect it somewhere, or we can even provide a GSM router on board of the vehicle, where you can upload the data to your database automatically. So you wrap up all cables, wind them up, close doors, and drive away to test your next test object. That was all from my side. I think you can find the video in the better quality on YouTube. I will provide the link here in the chat box. Thank you for your attention. Are there any questions?
Thank you, Dennis. That was a really wonderful video that you show that showcase most of the functionality and benefits of having a test van. So we're having only one question asking if this test van is available in Qatar or how it can be hired. I think this answer to this question, we will relate it to our sales teams to go through that process.
Exactly.
Yeah.
I can say that definitely we do have a number of demonstration vehicles on different continents. And I can say that we have a vehicle in Europe, in the US, in India. So it's just arrange logistics and bring it to the particular country. Of course, there will be some custom requirements and documentation involved for temporary entry of goods. And but these things are under control. We have experience of bringing these vans to different countries. So if you have an interest, we can definitely arrange this.
Sure. And I can say from Middle East sales team, we have dedicated guys for this. We will maybe contact the customer directly who are inquiring about this and give them further details on a later stage. As for other questions, it seems that we don't have any really other than this inquiry. And also we have reached the end of time for our session today. So for anyone who are leaving us, please feel free to submit the feedback form. Your feedback is very important for us. This is one of the first events that we conduct virtually that have really a wonderful panelists from all over the world. One thing I would like to mention before ending as well, that the recording of these 2 days will be sent to you automatically in 1 to 3 days, working days from the WebEx system, and also a certificate of participant in this conference as well, with a thank you from our side as well. Just to give more chance for attendees, if they have any questions, we have, I would say, a panelist of experts with us today on the topics that have been presented in the last 2 days. If also we would like, we can open the mic for some participants as well. If that makes it easier for them to ask the question, you just simply click the raise hand button and we'll see if we can open the mic for you to ask the question directly. There is a question for us, I believe, the organizer. Can you arrange similar session for motor and generator testing? I believe we do have another event similar to this that will be mainly focused on motor and generator testing. And that event, I will believe, will be conducted on the 20th and 21st of September, next month. So if you would like, we can share the registration links with you in the chat for that as well.
Hi, can you hear me?
Yes, we can hear you.
Yeah, thanks. Thanks for the opportunity. I just wanted to know if we have a transformer we make and we don't have any reference SFRA report of the ABB, then how can we just analyze the report, or just we refer the IEC document stating the ABC region of the curves, or what can we do if you don't have any reference SFRA documents from the manufacturer? Thank you.
I would suggest if Roberts can reply to that one. If Roberts is not available, I can answer to that question.
I didn't hear properly. I don't know.
His question is basically he has a power transformer without a benchmark for SFRA testing. So how
Yeah.
can he perform the analysis on such
Okay.
transformer without a benchmark?
Okay. Yeah, the benchmark is often a problem when you don't have it. So what I would do if I was in this place, I would do anyway a proper measurement of all three phases, open circuits, short circuit, and all other windings, and start to compare the phases in high voltage winding side and low voltage winding side, and see if there are like large differences. If there are minimal discrepancies, which is normal, then I would say, and otherwise, if transformer is fine, then I would say that this could be my benchmark for the future then.
And I could add a little bit more to that, like Roberts was mentioning. You can do a symmetrical phase comparative analysis on the same transformer. The other question is, if you have only one transformer like that one, maybe there's a sister transformer that has a similar nameplate, same manufacturer, and you can compare traces. That's another way to look at it.
Yeah.
And finally, the best thing that you can do is perform the test and send it to us, and we can take a look and talk to you and try to analyze it together.
Yeah, that is also a possibility.
Of course. We welcome your questions, and if you have some test results that you want to get some hints about the analysis, please contact your local Megger technical support, and we'll be more than glad to assist you.
All right. We have another question or raise a hand from Mr. Suman Jana. Your mic has been unmuted. Please feel free to ask.
Thank you. I have a question to Diego, actually. This is that yesterday I asked you about the C2 variants acceptance criteria. You told for C1, for the bushings, it will be 5% of the nameplate ratings. For the C2, there is no such limitations you told, but it should be compared with the other three phases. But is there any idea if the difference is maybe 200% with the nameplate results for the C2? Is it okay, acceptable? But all three phases are same, almost 200%, 210% within this.
Okay, thank you for your question. Again, when we talk about C1 and C2 on the transformer, some of the manufacturers don't even look at the C2, right, and recommend to be careful about the analysis based on C2. What is important to see is that, of course, your C2 capacitance is basically the capacitance between the test tap and ground, and that might be the layer that is most external, right, on the graded capacitor of this bushing. The other thing is that, especially because of the bottom envelope or the bottom part of your bushing, it's immersed in oil, or it has the connections, right, and could be shielded. There are so many different constructions, and that's the reason why when we were talking about the analysis based on C2, I did mention that you can take, for example, an OIP bushing, right, and do the testing outside of the transformer. But when you install that bushing in the transformer and you put that already in oil, you will see that there might be a difference on your C2 value, right? And if the other issue is that most recently you may have seen on the nameplate the C2 value. For the older bushings, you may not find the nameplate for C2, power factor, or capacitance because it may change. Like we were mentioning yesterday, right? You have 3 bushings similar by construction, by installation mounted on your transformer. The ideal is to do a comparative analysis between all of them, and most probably you will have a similar value for all the C2. I wouldn't say that a 2 times or a 200% is critical or not. What I would say is not only the nameplate, but the installation file, the commissioning file is the one that I would look at the most for the C2. Okay, but main assessment will be on your C1. There's some specific bushings. For example, you need to understand 2 things. You may have a test tap and you may have a voltage tap. So the construction of those 2 is also different. I think that we can have a session just on bushing assessment. It's a very interesting topic, and what I would like to do, Mr. Jana, is to probably send you a couple of papers that we have published about bushing assessment and validate with some additional information from different manufacturers, especially related to C1 and C2 analysis.
Right. Thank you, Victor, for detailed answer. We have another question. Someone asking in the question chat to open the mic. Mr. Adil, your mic is open now, so please go ahead and ask your question. We could not hear your question, Mr. Adil. Seems that you're either still muted or the sound is not coming. Seems that there is a problem with the mic that he's having. I don't want to keep you, the panelist, much longer than this, unless you have no problem with that.
If there are questions, we're here to answer.
I would like to, Mr. Adil, if you have the question, type it in if possible, to read it out for them and have the question right now. But if that's not possible for him, we can communicate via mail to discuss his questions even in more details for that. I would like to keep attendees and also the panelists more time than the assigned for them. So in the end, I would like to thank everyone from the panelists, attendees, and also marketing team for hosting and arranging this event. It's been a pleasure. Myself, I enjoyed and I learned a lot from the conference here. We will be conducting another similar conference for motor testing on the 20th and 21st of September. That will be having very interesting topics and speaker as well from all over around the world. And on the 4th and 5th of October, we'll be conducting another as well event for switchgear testing with the same format as well. So on behalf of Megger Middle East and all of Megger, I would like to thank everyone again for this great event, and I wish that you all have a wonderful day. Thank you, everyone, and goodbye.
Thank you.
You, Ali.
Thank you, everyone.
Thank you,
Thank you.
everyone, for
Bye
attending.
bye.